Greetings 213. In this video we're going to discuss section 10.5, abuses of statistics. We've already talked a little bit about how data can be manipulated or presented in such a way so that certain generalizations about the population can be made when in fact those generalizations aren't necessarily true, or certain conclusions can be drawn when that's not a good conclusion to draw from that data specifically. So it's important for us to realize that these are concerns that are important in terms of our principles and standards when we're teaching in K9. These concerns and ideas about how data can be presented and drawn and how we can draw conclusions from it appropriately, these are found in the NCTM principles and standards. This discussion here about data appears on page 48, and it says that the amount of data available to help make decisions in business, politics, research, and everyday life is staggering, and I think we would all agree that there are a lot of statistics that are thrown around in society that help sell products or help us make decisions about things, and how we make those decisions is really important, and we want to make sure that those statistics are being used appropriately and not misused. So, for example, consumer surveys, which are sent out to get responses to questions, these help guide the development and marketing of products, from everything from toothpaste to diapers to cars. And even in the field or the realm of politics, this happens. Polls specifically help determine political campaign strategies. How a candidate appears to the population can be determined based on polling. And also, experiments are used to evaluate safety and efficacy of new medical treatments. Not just these kinds of situations. Experiments are also conducted in terms of manufacturing as well. But it's definitely one of the places where safety and medical treatments are found that experiments are made use of, and the statistics and results of those experiments help determine whether new treatments are made or new products or services are given based on those results. Statistics in from these results are often misused to sway public opinion on certain issues or to misrepresent the quality and effectiveness of some commercial products. So they could say that some toothpaste is better cleaning than another toothpaste just based on some statistics, whether that's an appropriate conclusion to make or not. So an interesting quote from a 19th century philosopher and activist and thinker was that there are three kinds of lies. There are lies, damned lies, and there are statistics. And for a lot of people, there really is a lot of mistrust and skepticism about statistics because of their ability to be manipulated. So let's see if we can try to just be a little bit skeptical and a little bit conservative when we're being asked to believe certain statistics. And it's also good to get our students to think about these kinds of things also. So some people deliberately use statistics to try to mislead others. This can be especially seen in advertising. Now, whether it's malicious or not is up for discussion. But more often, what happens, however, is that the statistics are misused, right? And most often, this is the result of misinterpreting what the data or the statistics are actually meaning. It's usually not a malicious situation. Usually, it's just an inappropriate conclusion is being drawn from the data, from the statistics. The mean or the percentage or something is saying something, and you draw a conclusion which isn't appropriate to draw from the data. So let's consider an example. Consider an advertisement reporting that of the people responding to a recent survey, 98% said that Buffepain is the most effective pain reliever of headaches and arthritis. This is a really common statement to see for products. You'll be given some sort of percentage here, making a claim about some kind of product. And what's missing here is a whole lot of information about the survey, about who they asked to have this survey completed, about the pain medicine specifically here in question in general, and some other things. Let's consider some of the things that we're missing in a list. So in order for us to really be able to interpret what this 98% really means, right, to certify that this isn't being misapplied or misused or misinterpreted, really the rest of the information that should have been reported included the following. They should have included the questions that were asked in this survey, right, so that we are sure what people were responding to. They should have included the number of people that they surveyed. We don't know if this was a very large survey or if it was just 3 people that were asked. That's definitely important. The number of people who responded is also important because asking 3 people doesn't mean that 3 people answered. Asking 1,000 people doesn't mean 1,000 people answered. So even just saying the number of people surveyed wouldn't be enough. We need to know who actually responded for the survey. Also, how the people who participated in the survey were chosen. That's definitely important because we need to know if the sample of people that did the survey were biased or not biased. That can have an effect on what that 98% means. The number and type of pain relievers tested, that also is important because if they didn't test any other types of pain relievers or ask about any other types of pain relievers, then maybe the questions were a little bit biased. And finally, how the answers were interpreted should definitely be discussed. How did they interpret the answers to the survey? So without the information listed, many of the following situations are going to be possible, all of which could cause the advertisement to be misleading. So these are some of the ways, some of the examples of the concerns that we might have about this survey. So if we weren't given more information, we could hypothesize and say, well, this maybe could have happened. So for example, we could suppose that 1,000,000 people nationwide were sent the survey. Again, we don't know how they chose those 1,000,000 people, but let's just say they did choose 1,000,000 people to send the survey to. And let's say, what if only 50 of them responded? Well, that's, first of all, not a very good turnout, I would say, right? This would mean there was only a 0.005% response. That should cause us a little bit concern about that 98%, because what happened to the other almost 1,000,000 people, the 999,950 people that didn't answer? Why didn't they answer? Okay, that's definitely something we could consider, like, why didn't other people answer? Another concern or hypothesized sort of situation would be, suppose a survey sentence read, Buffepain is the best pain reliever I've tried for headaches and arthritis, and there were no questions about the kind and type of any other pain relievers tried. So maybe they were not asking if anybody had tried any other kind. So maybe people had only tried one kind, and so they had nothing to compare it to. So that definitely would create a bit of an issue with our survey if they weren't able to compare it to any other type. Of course, it would be the best because they haven't compared it to anything else. Let's consider the following issue. If of the 50 that responded number one, they sent out 1,000,000 surveys, 50 responded. Suppose 49 of the responses were affirmative. So let's say 49 out of those 50 people said, yeah, Buffepain is the best medicine I've ever taken for pain or headache. So the 98% claim is true. 98% of the responders did say Buffepain was the best. 49 out of 50 is 98%. But the issue is that there is no mention of the 900,000+ people who didn't respond, and that's a very big issue, given that we're claiming almost 100% affirmation that Buffepain is the best, when there's almost 1,000,000 people who chose not to respond, and we could, make conjectures about why they did not respond, and that should have an effect on that 98%. So let's also consider whether the sample was biased or not. So suppose all the people who received the survey were chosen from a town in which the major industry was the manufacture of Buffepain. So if they only sent the survey to the people living in the town where Buffepain is made, it's manufactured, all the people work for Buffepain, it is really unlikely that they're going to be able to get an unbiased response about that survey. Of course, they're going to say Buffepain is the best thing they've ever had because they're getting their paychecks from Buffepain, and success of that company is important to them, retaining their jobs in some cases. So it's really doubtful that to get an unbiased sample if the people were chosen sort of in a very localization kind of way, especially for production of a product like that. Lastly, so suppose only 2 pain relievers were tested, Buffepain, whose active ingredient is 100% aspirin, and a placebo containing only powdered sugar. So if an experiment were conducted and patients were asked to take Buffepain for a headache and then later asked to take another pain reliever, but they didn't know it was a placebo. Of course, the responders are going to say Buffepain handled the pain better than the placebo did because the placebo doesn't have any aspirin in it. It doesn't have any pain reliever in it. So this is sort of a mocked up or skewed experiment in which you're going to get for sure the response about Buffepain doing a better job because there isn't any pain reliever in the other supposed pain reliever. So that's an example of how a statistic, just in terms of a number, can be misinterpreted or misused. But there's also a different type of misuse of data in statistics, and this is involving graphs. So among the things that we need to look for here in if a graph is being misused are the following. One, if there's no title, what that means is that you have to interpret what the graph is depicting, and we should never have to do that because interpretation is going to lead to misrepresentation. And I've told you before how important a title is for a graph. Two, if there are not any labels on the axes of a line or a bar chart or on sections of a pie chart, again, you have to try to interpret what those sections or axes mean, and, misinterpretation comes from lack of enough information. Three, the source of the data. So if we're not told where the data is coming from, who was surveyed, or what the survey was like, or those kinds of things, then we're having to, again, interpret and come up with information ourselves that wasn't there. If there's not a key to a pictograph letting you know what the symbols actually stand for, then again, we can't really interpret what the picture is meaning. Also, be aware of if in the pictograph the little symbols are not there in a full picture. For example, with the newspaper example we talked about in class, half a newspaper is kind of difficult for us to interpret because we don't know if it's exactly half or a little more than half or a little under half. Uniform size and symbols in a pictograph is definitely important because if we don't have a uniform size of the symbols, we can't assume how much larger one is than another and what that difference in size actually means. If there's no scale, or if the scale is not clearly labeled, that's a problem. Also, does it start with 0? If not, then we need to be really aware with that. If it doesn't, is there a break shown so that we have some sort of perspective on the scale? Is the scale labeled so that the numbers are equally spaced? That's definitely important because, again, on a number line, we're concerned with making sure that the unit, the number 1, is very clearly understood, and the equal spacing between numbers should represent an equal distance between those numbers. So let's look at a couple of examples. Here we have a couple of graphs. Let's look at this left one first. So the title is here, number of girls trying out for basketball. The axes are labeled schools with number of girls. We have a scale clearly labeled no break, so it assumes it starts at 0. We've got a bar graph here. It's not a histogram, it's a bar graph because, again, it's not important on the horizontal axis, the order of these 3 bars. You could switch them around, it doesn't matter. And as it's sort of written like this, it doesn't really show that there's any major difference between these 3 schools in terms of number of girls trying out for basketball. It appears that they're all about 50 to 60. So in terms of our perspective on what's going on here, we don't have sort of a feel that any of the schools are different from the others in terms of the number of girls trying out for basketball. There's no huge difference between the 3. Now let's consider the second graph. Notice over here what they've done is they've changed the scale. See this, the break in the line down here means that now our scale is starting at 50 here. Notice that what they've done is take each of the tick marks to mean 2 versus over here where the tick marks meant 10. Okay, so what they've done is they've sort of altered the scale to sort of zoom in on the differences happening up here at the top of the bars. Again, the results of the bars are all about 50s to 60s here, 50 down here for Lincoln, all the way up to 60 and change up here for Wilson. But notice that in terms of our opinion of what's going on in the situation for these 3 schools, we now maybe are a little concerned about what's happening at Lincoln. Just the psychological aspect of this graph makes us wonder, like, is there something at Lincoln School which is prohibiting or preventing or discouraging girls for trying out for basketball at this school? Is there something going on? Are girls not being encouraged to try out for basketball at Lincoln? Or are they doing more at Wilson to try to get girls to try out for basketball? So now it's sort of psychologically making us feel like there is some major difference between Wilson and Lincoln, or Taft and Lincoln even. We're starting to wonder what's going on between these 3, where over here there wasn't that sort of psychological implication. That can also be seen here in this line graph representing number of graduates of community college. If the scale over here is labeled so each tick mark is 10, notice the break suggesting it begins at 130, then as it's written, we sort of see this steady increase or incline in the number of graduates of community college all the way from 2004 to 2007, but then we see this sharp decline in 2008, and that really makes us wonder what happened to sort of cause there to be so fewer graduates in 2008 than 2007. And really, it's not that there were so fewer, because really it was just 50 fewer. But the way the scale is labeled is making it feel very psychologically meaningful that there's such a steep decline here. If the scale was relabeled over here, it seems much of a less imposing decline here. It seems to be more of a gradual sort of just a slight decrease, and that's all because of the scale here. And notice that it's also a smaller graph too, right? Because they have made it now each tick mark meaning 50 instead of 10 as in over here. Okay, they've also, by the way, notice spread out the horizontal axis between the two graphs, yes? So that again, it's a more gradual arcing shape instead of such an up-down kind of shape. The psychology is kind of different. The psychological message is different. Sharp increase, sharp decrease, gradual increasing and decrease. So another error that often occurs is this use of continuous graphs to depict data that are discrete. And we've talked about this before, this idea of can we connect the dots all the time? Does it make sense to connect them and use a line graph? So for example, here in this graph representing enrollment patterns for a certain math class, we've got bars here representing each of the semesters, fall and spring, for it looks like 2.5 years. Now, we have everything nicely labeled and everything, but it would not be appropriate to take the data points that would have been represented here at the tops of these bars and connect them with a line. The reason that wouldn't make any sense is because, let me use my pointer for a second, connecting them assumes that there are data points that would be represented by each of the little dots here on this line. And remember, a line is made up of infinitely many points. So there could have been a data point, for example, right here, right? There might be meaning to that point right there. For example, there is a term between fall and spring term. It's called winter term, right? And so there could have been a meaning to maybe this dot right here, which would be the value or the enrollment in winter of 2007, right? Winter term of 2007. That could have been the value there. However, what about like this dot right here? Yes, or what about this dot right there? Do those dots have any meaning? Is there a term between fall and winter term? Well, no. Is there a term between winter and spring term? No, which means that all of these dots that make up this little bit of this line segment right in here, those are meaningless. They have no value. They don't have any interpretive meaning for us graphically. So connecting the dots in that way wouldn't make any sense. Also, another way to distort graphs is to omit the scale. Notice here on this left graph, we have all of these lovely bars showing that enrollment patterns at Cuyahoga, I think that's what that is, have been increasing since 2004 to 2009. Do you have any idea, without a scale here, what kind of enrollment increase they're seeing? Have they gone from 1,000 students to 10,000 students? We don't know what the growth is here. We would have to sort of just assume what they're doing here. And I mean, it appears like it's a fairly good growth that they're seeing in those 5 years. When they apply the scale like they should have originally, and we're able to see what's happening, it turns out that they've actually only experienced a 40 student growth here, right? So in 2004 it was at 8,010, and in 2009 it's at 8,050. They've only increased their enrollment by 40 students. That's not really what we would have assumed over here, a growth of 40 students. So it's definitely important to have a scale, but quite honestly, a lot of the time a scale gets tossed out so that you can try to imply or misuse the graph to imply a greater growth than actually what occurred. So another example of graphical or visual misuse of these graphs is an area model. So let's suppose the number of boxes of cereal sold by Sugar Plops last year was 2 million. That's these guys right down here. Notice the height of the box is 2 to suggest the 2 million boxes, right? And the number of boxes of cereal created by Corn Crisps was 8 million. Notice that what that means here is the height of this box is 8 to represent millions of boxes. Does the horizontal axis have a scale? No, it does not. So the width of these boxes is not like it's like a box plot at this point, right? We have a box graph. I mean, we have a box graph at this point where we're just representing the kinds of cereals here, and the height of the box represents the millions of boxes. We just have a box graph, a bar graph. So the bar graph that we have shown here just represents the height of the boxes represents number of boxes sold in millions. So we're kind of just being fooled a little bit here in terms of thinking that there's so many more boxes of Corn Crisps being sold than Sugar Plops, because ideally what it should be, if you're going to use this kind of area example here to show one being significantly more than the other, is you should agree with what the data says here. The number of Corn Crisps and the number of Sugar Plops is actually only differing by a factor of 4, right? So Sugar Plops was 2 million and Corn Crisps was 8. So it's really 4 times as many Sugar Plops as Corn Crisps. And so what that means is this gold box should really be 4 times as big as the blue box, and it's not. Right? The area of this bar, this box here representing Corn Crisps, is actually 16 times the area representing the Sugar Plops, rather than 4 times the area, as would be suggested by the original data. Okay, and so that can skew us into thinking there's many more Corn Crisps than Sugar Plops. Fixing this would be to make the boxes or the bars have the same width, right? That would fix it. Another abuse of statistics is with circle graphs. Circle graphs become easily distorted when you depict them as three-dimensional, when you sort of lay them back instead of looking at them more flat. Like, let me draw you an example. Instead of looking at them flat like this, where you have just these segments like this, with no three-dimensional perspective on them like this. Yes, this is a two-dimensional version. This is a three-dimensional version where it's kind of been laid back like this. When this happens, it gives you a false impression that certain sections are larger or smaller than they really are. For example, this green section here in the front, this 27%, should actually just be what? About a quarter of the entire circle. But when it's laid back like that, notice that this area here, and especially when you see visually just some extra green stuff here, right? Just even more green sort of skews you into thinking that there's this section here seems to be bigger than just what would be representing a quarter of the actual top circle, right? It should be about a quarter of the top circle, but just because of perspective and sort of, if you know any art, sort of the line of recession kind of thing, sort of vanishing off into the distance kind of idea. Things in front appear larger than things near the back, right? So the section in front appears larger just in a distorted way because of the perspective that's being given on the pie, because of laying it back like that in three-dimensional space. So the final examples of the misuses of statistics involve misleading uses of mean, median, and mode. All of these, remember, are averages, mean, median, and mode, and they can be used to suit a person's purposes. They can be, you could use one versus the other in order to try to mislead the population that you're giving the data to, or something like that. And the important thing to watch for when a mean is given specifically is disparate cases in the reference group. What this means is if there are high upper extreme or high max values, or very low lower extreme or small values, right? So outliers is really what this is referencing here. And especially if the sample is small, right? If the sample is small, a few extremely high or low scores can have a great influence on the mean. And this actually we've already seen when we discussed the salary example with the company that employed 20 people. There were 18 people that made $10,000, a president that made $200,000, and a vice president that made $75,000. And remember, we found that the mean was in the $20,000 range, but that doesn't represent adequately or appropriately most of the people in the company. And the reason that mean got pulled up higher than most of the people in the company's salary is because of those two high outliers, the president and the vice president. Okay, so when there are a few extremely high or low scores, that mean is going to be modified and is not really going to represent what's going on. Okay, and those outliers don't have to be reported in a data set unless you're including all of your data. But quite honestly, most of the time those outliers will be just tossed out and the mean can be used or misused in certain ways. Okay, so just let's try to keep these abuses of statistics in mind, and also get our students to be a little bit cautious and thinking about when it's okay to take generalizations from our data and apply them to the entire population or make decisions using statistics.